put it in the record mode, and then I'll start sharing. Share. Okay, so I think now you can see the screen. Yes? Hello?
Yes, sir.
Okay.
Sir.
Yes, sir.
So we'll just
Yes, sir.
recapitulate what we did last time. Little bit, we'll go forward and then start. We were discussing about the stereochemistry of this 4 and plus 4 pi plus 2 pi cycloaddition, which is Diels-Alder reaction. So we have got different aspects of stereochemistry. One is diene need to be present in SC's conformation. This is what we see. I've explained it last time, so I'm not going in the elaboration of this. Then in stereochemistry, that means the addition will take place in scene stereochemistry. That means the reactant, if they are in cis configuration, it will remain cis. If it is in the trans configuration, it will not. It will remain as trans. It will not alter. This is what we find. Then we come to endo condition, endo addition. That means the product for this type of a cyclic diene and this dienophile, which may be cyclic or maybe acyclic. This product is an endo product, and this is going to be exo product when it comes to this particular configuration. So that one, exo is supposed to be thermodynamically more stable, but what we find, the endo product is the major product in these cases. Reaction take place under thermal conditions. We'll come to theory again when we'll discuss the other point. Okay. So this endo is both thermodynamically unstable. Endo is thermodynamically less stable, but this case endo product is major because the reaction proceeds through a transition state which is more stabilized when this dienophile comes in the endo position, attacks through the endo position because of secondary pi overlapping. So let us see this. These things, I think you should remember. This is the from the theory part. What happens? A diene will give its electron to the dienophile, diene from the HOMO of this diene to the LUMO of dienophile. So it is the transition state will involve that HOMO and LUMO. And so it is the energy difference between the HOMO of diene and the LUMO of dienophile. Now in this case, what is ground state and excited state? That means ground state is this diene has got four pi molecular orbital, psi1, psi2, psi3, psi4. Psi2 is the highest occupied molecular orbital, but under photochemical condition, psi3 becomes HOMO. And what is the orbital orientation of this psi1, psi2, psi3? Already you know, this is without node, 1 node, 2 node, 3 node. So psi1, psi2 is HOMO under thermal condition. That means when the electrons are in the ground state. But if it is in the excited state, HOMO becomes psi3. In psi2 and psi3, the difference is that in psi2, these terminal loops, because the bonding has to take place through these terminal loops. I think we are here. So let us see here. So Psi3 is antisymmetric, Psi2 is symmetric. But when we come to alkene, simple alkene, the ground state is Psi1 and Psi2. HOMO is Psi1 in the ground state, that means under thermal condition. But in the excited state, this is it is in the Psi2. HOMO is Psi2. And here what we find, what is Psi1 without any node? Psi2 is with one node. So that will be antisymmetric here. This is symmetric here. Let us see this. The reason for endoproduct formation, transition state of the concerted reaction is more stabilized due to secondary pi orbital interaction. Now you see here, uh, this is the antisymmetric Psi2. The reaction condition is thermal. Uh, so they are going to overlap. This is same phase. This is also same phase. But this extra pi electron which is there also going to have an overlap, a secondary overlapping. And when this dienophile is in endo position, attacking the endo position. When it is exo, this group come this side, so there is no secondary overlapping. So this is why this one in the endo product is more, because the transition becomes more stabilized. As a result, the reaction is kinetically controlled. Though the product is exo product is thermodynamically more stable, the product form is endo because of this. Okay. Now we come to regioselectivity in Diels-Alder reaction. First one was stereoselectivity. Now it is regioselectivity. I think you know what is regioselectivity. Say in case of what is, can anybody give some idea about what we mean by regioselectivity? Hello? Can you give some idea about regioselectivity? Say in Markovnikov's addition, when we take Markovnikov's addition of bromine in propene, suppose HBr in propene, what we get? 2-bromopropane, right? That happens because of the
Yes, sir.
that is it comes to the more less substituted bromine comes to the less substituted less carbon with the less number of hydrogen, and you know the reason why it happens, because of that stability of the carbocation that is there. So this type of selectivity, when it is there, that is called regioselectivity. There is now here let us see what are the, suppose here diene and the dienophile are unsymmetric. The diene is having this substitution here, and dienophile is having another substitution here. So the two possibilities which are there, it may be 1-2 adduct, this R and COR prime will come here in the 1-2 position or in 1-3 position. This is one. And let us see the variation which are there. When this type of substitution and E, so first one, second with this R and R prime having this type of variation, what we find 1-2 is 100%, here 95, here it is 100, here it is 50. So with this RCONA, this is 50%, and 50, the 1-3 is again 5%. That means here the yield is also low. All right. We have to understand why it is happening that way. If your substituent of this type, the substituent is of this nature, that means in the R group is there in the position 2, this one, then the product may be 1-3 or 1-4. 1, 2, 3, 4, 1-4 position, or it may be in the 1-3 position. That means either it is attacking this one with this one, that becomes a 1-3, or this one, this carbon with this carbon, that becomes 1-4. Right. So And here, let us see what is the position here with this R, different R we have here, OET, pH, CN. This distribution is like this. That means 1, 4 is more than 1, 3. Let us have a reasonable explanation for this. With the FOMO theory, what we say this HOMO and LUMO, because interaction will take place between the HOMO and LUMO, interaction governed by atomic orbital coefficient. Atomic orbital coefficient at the terminal atom of the diene and the diene. Okay, let us quickly come to this one. This coefficient is difficult to understand. Now, when this is COOH here, and this one is also COH here at this in the diene. Now, what is COH group? COH group is an electron withdrawing group. Here also it is an electron withdrawing group. So what it is going to do, it is going to withdraw electron. As a result, and this, you see, these are the terminal lobes are antisymmetric here and also antisymmetric here. This is HOMO. HOMO is antisymmetric here at the terminal atom, and this is also LUMO is also antisymmetric. But which way it should they should combine? Now here the electron density decreases. This one also electron density decreases. The overlaps. This what is called in a very simple way we can take that this two orbital may be of the similar size. If this is lower size, this becomes higher size. The size is so they will have more compatible size this side. The compatible size will be this one. So this bonding will take place through this one preferably. So we have 1, 2 as the dominant adduct. 1, 2 adduct is dominant. And this is what we see here from the earlier data. COH is COOH is R is COH and R prime is H, because that was in the general it was given as R prime. So R prime is H here at temperature 70 degree. 1, 2 product is 1, 2 adduct is 100% and 1, 3 is 0. So it is telling with that one. Let us see to the other side. If there is there is a substituent here at this position, phenyl, this orbital size and this orbital size becomes equal, and this one becomes less, and this is also less because of this electron withdrawing group here. So now the overlapping will take place through this, and this one will overlap with this one. So we get 1,4 product as the major product. 1,4 product as the major product, and we get this. And here from the result also we find here 82% and 18%. 1,3 is 18%. So this is one of the explanation for this. Okay, I'll be forwarding this one, and you can read it. This is not very difficult to understand.
Sir.
Yes. Yes. Tell me.
HOMO and LUMO interaction.
Yeah.
From 2 pi system.
Yeah.
HOMO is psi 1. And in case of 4 pi system.
No, wait.
1 is psi 4.
But what is the interaction? An interaction between HOMO of diene and LUMO of dienophile. And LUMO of dienophile is psi2 in ground state, and HOMO of diene is also psi2 in for diene. And diene is antisymmetric at the end. Here also it is antisymmetric at the end. That means the lobes are of opposite, terminal lobes are of opposite phase. You have to see the picture. Yeah, I think you should keep that chart in front of you, because I cannot just go and then again and again and refer to that one. Every slide I cannot have that one. You should have that chart in front of you. All right. Okay. We'll talk about the theory again more. Let us come to the next point. Okay. This is again this. Okay. This is what again because of this. I have again put it here. This slide today. You see here. This is the ground state HOMO, and this is LUMO is Psi2. What is Psi2? Psi2 is this. What is Psi2? This is antisymmetric. You see here. The terminal lobes are antisymmetric. And in case of diene, the diene's electrons, there are 4 electrons, there are 4 pi orbitals, 4 electrons, but 4 pi electrons, which are orbitals are Psi1, Psi2, Psi3, Psi4. But 4 electrons, how they will be present? 2 will be here, 2 will be here. So Psi2 becomes HOMO. But when you excite it, 1 electron goes from that to Psi3. In the excited state, this becomes Psi3. And what is Psi2? Psi2 you see here. This is Psi2. The terminal lobes are antisymmetric. And what is Psi3? Psi3 is terminal lobes are symmetric. So what happens in case of 4+2 cycloaddition? It is it is the ground state. The reaction takes place under thermal condition. We are coming to that one again in our discussion. All right. Any question? Yes.
No, sir.
Okay. Let me proceed.
No, sir.
Sir,
Yes.
sir,
Yes.
I have a doubt.
Yes. Follow.
That previous slide you have written that COH and COH. That sir, please go to the previous slide.
Yes. Yes.
The first reaction, sir.
Yes.
In both dienophile and diene, we have COH. Sir,
Yes.
here we will go for the orbitals only, or the
No.
that
Homolo,
withdrawing effect also.
just listen. Homo LUMO is going to be the same. Homo of diene and LUMO of dienophile. And homo of diene is also
Yes,
antisymmetric. Now here, this black sign and white sign that we are seeing, it is showing that different phase, opposite phase. Diene also is opposite phase, but
yes,
you see,
sir. But
yeah. What is the question?
But sir, if COH is in one position, then if we think about resonance or something, then the next terminal we will get a del plus.
Now you see here, this is
And
electron withdrawing.
in case of dienophile also, we will get a del plus. Yes,
you
sir.
see, just a minute. So what del plus means what? Is going to be electron density has decreased or not? Del plus means electron density has decreased. Huh? When electron density is decreased, what happens to the orbital size? Orbital size decreased or not? Orbital size.
Yes, but in both cases, same terminals will get del plus and del plus.
Yeah.
So how can?
Wait. You don't go by that. Wait, don't go by that. Here it is not an. Here it is not an what is called electron. What is called is not an ionic reaction. We are going of the what is called orbital symmetry. Orbital symmetry, overlapping. Don't go by that delta plus and delta plus are interacting. No, it's not that way. Because of the delta plus here, the size of this orbital is decreasing. Previously, if it is big size, now it has become small size because of that electron density.
Yes,
now this is also small, this is also small. So two small overlapping will be better than one small and one big. Yes or no? This is what is your coefficient.
Yes.
This is coefficient, orbital coefficient. this is not going to do with your delta positive and delta positive interaction. It's not an ionic reaction. Got my point?
Yes, sir.
It's not an
Yes,
ionic
sir.
reaction. All right? I think that you
Okay,
have
sir.
to consider
Yes.
that way. Okay.
Sir,
Let us come to 2 plus 2 cycloaddition. So when we have seen 4 plus 2 cycloaddition, what it was? It was thermally allowed. Thermally allowed. Because orbital symmetry has to be maintained. Same phase orbital has to come together, because we have seen for p orbital there are 2 phases. If there is one, if we shade it, and this is unshaded. If the 2 orbitals come with the same shape, same phase, then only overlapping will take place. If overlapping take place, then it is going to be bonding. If the 2 opposite phase comes, suppose this is of this phase, the other one is coming with an opposite phase. Here, this is not going to be a bonding. So this is how the bonding takes place. In case of 4 plus 2 cycloaddition, what we have seen, the reaction takes place under thermal condition, because of that I mean, homo of diene and lumo of diene has got that orbital symmetry comes out. We come to cycloaddition. Let us see under thermal condition what is the situation under thermal condition. So here also, here 2 plus 2, that means 1 is 2 pi. What is your psi? What is your homo? Homo is psi 2, right? What is your lumo? Oh, sorry. Homo is, if it is ground state, so homo is psi 1. And what is lumo? Lumo is going to be psi 2. Yes or no? What is shomo? See here. Ground state. Homo is psi 1. And the other one is also a diene, alkene. So its lumo is psi 2. When they come closer, when they want to interact, what is this one? This one and this one same phase. So there is bonding here. But this one and this one are opposite phase. So there is no bonding here. So this reaction is not going to take place. So we say that, what we say? Then we say that thermal 2 plus 2 is also another term I am introducing, S here. Pi 2 pi S 2 pi S is symmetry forbidden. This S is stands for supra. The opposite of supra is what? Can anybody give me the opposite of supra? You have heard this one in your, maybe in your college. Opposite of supra?
Enter.
Antara. Not enter.
interface.
Anterafacial, suprafacial. Supra means same side, you can say, and this one opposite side. So here the same side, and same side, if they approach you, it is not symmetric. So this is supra addition is forbidden, symmetry forbidden. And this one also we see here, homo of one diene with the lumo of another diene, not diene, alkene is not going to take place under thermal condition. So that becomes, so this is not going to take place. So it is symmetrical. So under thermal condition, no 2 plus 2 cycloaddition happens. Coming to now, under photochemical condition. Now, under photochemical condition, this is what you see. What is your, under photochemical condition, homo becomes psi 2, yes or no? Homo of psi 2, and lumo In the ground state, not that both excited state. You don't consider that both need to be in the excited state. Both, because when it is excited, when you say excited, electronically excited, photochemically excited, you give energy. Not that 100% molecules are going to excited state. Does it happen? You have studied photochemistry at different levels. Does it happen? No, not that 100%. If there are 100 molecules, suppose, or 100 atoms, all 100 atom electrons don't jump. You also know something called quantum efficiency and all. It is never 100%. So some remains in the ground state. So what happens here? Excited state, which is Psi2, and the ground state Psi2. You see here now, the Psi2 is antisymmetric in both the cases. And what do we find? This one and this one the same phase. So there is overlapping, and we get a molecule of cyclobutane. And this is what we say that photochemical 2 plus 2 cycloaddition, and here it is pi 2 supra and pi 2 supra is symmetry. You see S, this term is S, is supra. In same set, they are not going to alter their geometry. That supra is your symmetry allowed. So in other words, very simple way, photochemical 2 plus 2 cycloaddition is allowed. Thermal 2 plus 2 cycloaddition is forbidden. Let us see now another. However, thermal 2 plus 2 cycloaddition is suprafacial with respect. Thermal, you see, we are going back to thermal. Photochemical, we have seen it is supra cycloaddition, supra addition. But when we go to thermal, suprafacial with respect to one component and interfacial with respect to other is symmetry allowed, but geometrically 10 minutes more, geometrically difficult. Let us see again. Ground state. You see, the condition is ground state. What is HOMO? HOMO is Psi1. What is LUMO? Is Psi2. What is Psi1 was symmetric. Psi1 is symmetric. There is no lobe. And Psi2 is what? Antisymmetric. So there is this one and this one, opposite lobe, opposite what is called phase. Now here, if it has to overlap, what has to happen? This one and this one, they can approach from the same side. So this is suprafacial. But if it has to, suppose it has to overlap, then what has to happen? This is the front side, but this one is back side. So if it has to overlap, this one has to overlap with this face. But it becomes what? Opposite. So it becomes enter. So if you have to carry out thermal cycloaddition of 2 plus 2 cycloaddition, then what it has to do? One will be supra, the other one has to be enter. Supra enter is symmetry allowed. But because the molecule is so small, that twisting is not allowed, not possible, geometrically not possible. So it is geometrically difficult. This is the reason. Thermal you can carry out, provided this twisting was allowed. But it is not allowed because of the constraint of the space here. So geometrically it is difficult. I think you got it? Hello? In case of actually ketene and alkene, this is possible. So thermal cycloaddition is possible in 2 plus 2 cycloaddition. I think I have not included. So, next class I may give it if required. I have not included that one. Okay, let me see this next one. So this is what? This is your thermal, thermal is 2 pi supra, 2 pi entera is allowed. It is allowed, symmetry allowed, but geometrically forbidden. Geometrically forbidden. I think any that query is there, you can ask it. Let us come back to again 4 plus 2 cycloaddition. 4 plus 2 cycloaddition. Already, what is your HOMO? HOMO is your Psi2 ground state under thermal condition. Remember, thermal condition 4 plus 2. This is ground state is Psi2. Psi2 is terminal lobes are antisymmetric. So this is one and this one are antisymmetric, and is going to overlap with dienophile, but it has to be LUMO. In the ground state, dienophile is having antisymmetric. And now you see this one is overlapping with this, and this is overlapping. They are of the same phase, and they are approaching what? Same side of no twisting. So it is supra addition. Supra addition. So you use this supra. That means both are suprafacial with respect to diene and with respect to dienophile. Supra. So 4 plus 2 is thermally allowed, suprafacial with respect to both reactant and photochemically for. Okay, let us come to photochemical. In the photochemical, what happens? Your Psi3 becomes, your HOMO becomes Psi3. When we have already checked what was Psi3. Psi3 is now both terminal lobes are antisymmetric, symmetric. Has to overlap with the LUMO of dienophile. Dienophile is alkene, and whose is Psi2, and which is antisymmetric. Now here we find if it approaches suprafacially, what happens? This is overlapping, but this one and this one, suprafacial, is forbidden. No bonding is possible because of they are of the opposite. But it can form if it is coming enterofacial. So photochemical cycloaddition, 4 plus 2 cycloaddition will be possible only supra-entera possible. But again, the geometrically forbidden it becomes. So virtually, we don't have any 4 plus 2 photochemical cycloaddition reactions. All right? Hello? Yes or no? Because it is on only 5 minutes left. I have to cover some lot of things. I targeted a lot of things, but I don't know whether I can do it. So what is this one? 4 plus 2 cycloaddition is thermally allowed, suprafacial with respect to both reactants, but photochemically forbidden. What is photochemically allowed? Supra, entera is going to be photochemically allowed. So 4 plus 2 cycloaddition under thermal condition is, it is 4 pi supra, 4 pi, pi s and 2s. Actually, these are 2s also is not to be, 2s is not a very, 4 subscript s again. It's difficult to write here, so I'm not writing like this. And what is 4 plus 2 under photochemical condition? It is going to be 4s.
Forbidden.
And it is forbidden, but if it is to be allowed, it has to be 4 pi supra and 2 pi entera. Then it will be allowed. But this is going to be geometrically not possible. So this is forbidden, this is allowed. So both thermal, okay. So let us come to only 2 minutes left. Both thermal as well as, okay, let us come here. Both thermal as well as photochemical cycloaddition reaction take place by opposite stereochemical pathway. There is a stereochemical rules for cycloaddition addition reactions. Okay, this has become one sentence, one word. It has to be, there should be a gap. This is what is the chart. Now this, you see that. Under what condition, what will happen? The electron pairs means double bonds, not that total number of pi electrons. Electron pairs. It may be even number or it may be odd number. Even number, it becomes 4n, and it is odd number, a 4n plus 2. Under thermal condition, if it is 4n, that means even number like 2 pi, 2 pi, 2 pi, 2 pi, it is going to be interfacial. This is going to be suprafacial. And this is going to be photochemically allowed. And odd number, it is going to be suprafacial, thermal, suprafacial, photochemical, interfacial. The reaction happens under thermal condition. Okay, I'm just stopping. We'll come back again. You'll join back. You join back again. I'm just stopping this. Quickly, again, you join.